Assalamu alaikum and a very good morning to all. We welcome you. The Professional Development Committee of Utah's Nizwa is striving to bring forth more learning activities for the staff in and around Nizwa. We are privileged to present our PDC activity for this semester under the guidance of Dr. Sara Al-Bahlani, the Deputy Vice Chancellor and Chair of PDC Committee, supervised by Ms. Suad Al-Riami, Head of IT Department, coordinated by Ms. Turkiya Al-Busaidi, the PDC Deputy Chair. We have brought to you this PDC activity today. We welcome you all. We welcome all the participants from all departments and branches. Thank you for joining this event. We hope that you will find it extremely beneficial to your work. The moderator of today's event will be Ms. Alice Lontock, the head of Information Technology section. I hope you have a wonderful webinar time. Thank you. I would like to introduce the speaker of the day today, Dr. Ashwini Kumar Cherkuri. Dr. Ashwini Kumar Cherkuri is professor at School of Computer Science Engineering and Information Systems, Vellore Institute of Technology, Vellore, India. He holds a bachelor's and master's degree in computer science from Acharya Nagarjuna University, India, and a PhD degree in computer science from Vellore Institute of Technology, India. His research interests are information security, machine learning, and quantum computing. He was the recipient of Young Scientist Fellowship from Tamil Nadu State Council for Science and Technology. Also, he was the recipient of the Indian Express, India's leading English newspaper, Inspiring Teacher Award 40 under 40. He has executed few research projects funded by the Department of Science and Technology, Government of India, Department of Atomic Energy, Government of India, Ministry of Human Resource Development, MHRD, Government of India. He published more than 100 referred research articles so far in various national, international journals and conferences. He has delivered technical talks at several national and international conferences. He is the editorial board member for several international journals. He is a senior member of ACM. He has organized a 3-week summer school on informations and systems security in association with ACM India during May and June of 2017, which attracted students from across the country. We welcome you, sir, and we are really pleased and more privileged to have you in our PDC activity to give us the talk on Introduction to Blockchain. Thank you so much for attending this and to share your uh, very precious knowledge with us. Now the platform is all yours. You can share your screen and you can also start the talk. The moderator will be Miss Alice Lontock. She will be taking over from now. Thank you so much.
Sure. Thank you, madam. Am I audible?
Yes, sir, you're audible.
Okay. So I'll just, yeah, my screen is visible, right?
Yes, sir. Yes,
Yeah.
it's.
So at the outset, I would like to thank Dr. Sonia for the invitation and under the ACM Distinguished Speakers Program. In fact, we are interacting from quite some time and trying to make this talk, feasible. Due to some reasons, we were not able to make it. But now today, I'm happy that we could make this talk. And thanks to Dr. Sonia for all the efforts and arrangements that she has done. And also, I thank Dr. Alice for chairing the session. So the talk today is on introducing the blockchain technology. What are the various fundamental aspects, then the primitives that are behind the blockchains. This particular talk is made possible because of the ACM Distinguished Speakers Program. As a formality, I would like to briefly introduce the ACM. All of you may be aware that ACM is the largest professional communication professional body with more than 100,000 members spreading across 170 countries across the globe. So the mission of this ACM is to help the computing professionals to be their best and most creative in their tasks and jobs. This particular body connects the peers and inform the latest developments as well as inspire the professionals. The vision of this body is to see a world where computing solves the tomorrow's problems. I'm proud to be an ACM senior member, and I wish all of you to take part with in the professional community. And this particular talk is made possible under the ACM Distinguished Speakers Program. More details of this program are available in this dsp.acm.org website. Now, this particular session on a blockchain is going to provide these topics. Let me put forward. Number one, I'll briefly introduce what is blockchain, and then what are the fundamental notions, definitions of blockchain, then the crypto primitives behind the blockchain. When we understand the crypto primitives under the that are working under the blockchain, we will be able to quickly connect what are the core technology that is there behind the blockchain. And also we see one of the fundamental data structure behind the blockchain, which is the Merkle tree. We will see the working of this Merkle tree. Then also we see how the blockchains are created, creation of the blockchains. While creating the blockchains, there are certain algorithms that work in between. Okay, so we see those algorithms called consensus algorithms. Then we also see what are the conflicts that arise while creating the blockchains. So how to resolve the conflicts. Then we also see what are meant by forks in the blockchain. Then we see some of the applications. So this would be the agenda of this today talk. I hope this is okay to everyone. And the fundamental talk is tailored towards the undergraduate and postgraduate students who are actually getting into the details of blockchain. So we all know that there are certain transformations that are happened in the computing world, starting from mainframe computers. Then we have personal computers in 1980s. Subsequently, the another evolution happened in 90s through because of the internet. Then 2000s, we have witnessed a revolution of mobile as well as the social media. And subsequently, post 2010, we are witnessing one particular transformation called blockchain. And in addition to that, now there are some other transformations, including quantum computing and etc. But let us focus on this particular transformation, which is the blockchain, which has happened after 2010. Let us see what is basically the blockchain is providing. The blockchain is providing certain capabilities such as trusted transactions. It is also ensuring the security. We are able to track on real time all the transactions that are happening it. And above all that, if you see, most fundamental significant aspect is the unalterable transactions. Then there is no trusted third party or third parties that are getting involved. And because of that, there is a reduced cost in terms of economy, and there is no single point of failure. Unlike a traditional client server models, there is no single point of failure. And also it is providing transparency. These are all the features of blockchain technology. But what is blockchain? The blockchains are regarded as distributed ledgers, which are cryptographically signed, and these are all grouped into blocks. So each of these words have a meaning. It is distributed digital ledger. These are all cryptographically signed and formed into the multiple blocks. And when these blocks are connected, we have blockchain. So, in the sense, I can say that, we all know about the databases. And imagine these databases are distributed, and these distributed databases are secured through cryptographically signatures. And all these secured cryptographically signed blocks are connected. Then you can think that as a blockchain. Okay, so an informal definition or description of the blockchain is a distributed digital ledgers which are cryptographically signed and formed into the multiple blocks which are connected. And that's the reason why each block is cryptographically linked to the previous one. And this linking happens only after validation. And the validation happens through a algorithm or through a process called consensus. So this is the way we can actually describe a blockchain. And when new blocks are added, whenever the new blocks we are adding, they are getting into the adding into the chain. And once the transactions are added, then it becomes difficult to modify. So providing a feature called immutability. That means when once the transactions are recorded into the blocks, they are difficult to modify. Sometimes when we read certain literature, we also come to the notion that it is absolute immutability. But if you see here, it is carefully written as difficult to modify. Okay, so that means imagine if somebody have a huge computing power, it is still possible to modify it. Only thing is that they need to put an enormous power and effort to create the whole blockchain from the beginning. Then it is possible, but otherwise it is difficult to modify. And you see the next statement, the new blocks are replicated across multiple nodes. That means the multiple nodes in the network, they are all having the replicated copies of the chain. And hence we say that these are all distributed across. And during this process, any kind of conflicts that are arising, and these conflicts are resolved through some kind of a process. That's the point which we talked about, the conflict resolution. So this is the whole this particular slide in a very informal way talk about the blockchains. As number one, these are all distributed digital ledgers, wherein which it has set of transactions, and all these transactions are cryptographically signed, and these transactions are grouped into multiple blocks, and blocks are connected to each other through cryptographically. And before before these connections are happening, you have a process called validation. All this happens with the help of consensus. And this is the feature of the blockchain called immutability or difficult to modify. So this is an informal description of blockchain technology. So whatever I have narrated it, these are all the points. So when we say that you have a block typically containing set of transactions. So it's take an example, you have transaction one, transaction two, like this, I have multiple transactions. All these transactions, I can group it in the form of a block, and that block also will have a timestamp. In addition to that, there is a hash pointer. There is a hash pointer. We will see one particular block and then we can narrate. So that means along with the transactions, you have one more field called timestamp. Then you have a hash pointer pointing to the previous block, and also you have a connection to the next block. So in this way, you are having chain is getting formed by linking the blocks with each block. Why we are doing this hash pointer, we will discuss it a little later. So because of all these processes, blockchain is a robust, protected, as well as transparent ledger, because it is implementing the security features with the help of cryptography. And how this whole process starts? The whole process starts when you have a transaction. So imagine there is a transaction request from any user, which we can call it as a node. And all this happens in a peer-to-peer network. And when there is a transaction request, that particular transaction would be broadcasted to all the users in the network. So that means you are providing a kind of a transparency. Once the nodes in the network verify the transaction, how the verification step happens? Because of the, again, underlying cryptography, which is nothing but the digital signatures. So under verification process takes place, then once you have verification process happens, then transaction data would be put into the a new block. So a block may have one transaction or multiple transaction. It all depends upon the kind of application we have. So finally, a new block is connected to the blockchain. As I said, we have using the hashed value of the information presented in the previous block. So that is how blocks are getting chained. And in this process, you have a consensus, which includes the verification of the transactions before the transaction is added to the blockchain. So that means imagine that one node is proposing a transaction. It doesn't mean that the transaction would be added to the block. Instead, the other nodes, mining nodes or verification nodes, have to verify and validate the transaction. Then only the transaction would be added to the blockchain. And in this process, the blockchain grows without fear of manipulating of the blocks because of cryptographically are linked through the hashes. And in this process, typically what happens when the blocks are growing, there are possibilities for having the ledger conflicts. They need to be resolved. Similarly, there are chances for having the forks. That means wherever the blockchains need to be modified, you have two types of forks called smart fork and as well as hard fork. These need to these needs to be resolved. So this is what we discuss in the session. So in a pictorially, you can see that there is a node seeking for a particular transaction to be appended. So that particular transaction is to be broadcasted in a peer-to-peer network. So this is your peer-to-peer network. This is your peer-to-peer network. So when it is broadcasted to the nodes in the peer-to-peer network, they validate it. So the network nodes validate the transaction. When once the transaction is validated by everybody, then you have a block is getting created. And that block would be added to the chain. The picture illustrates for a single transaction, but you can have multiple transactions getting into a block. So that means you need not have only one transaction in the block, but rather multiple transactions in the block. This point we have already discussed. Number one, there are multiple benefits being increased transparency. We are able to accurately track the transactions. And another thing is, since it is cryptographically linked transactions, your ledger is almost permanent. And the maintenance of the ledgers, because you are making it in a distributed nodes, cost reduction is also happening. There are several application areas where blockchains are being now implemented, including the financial services, automotive, as well as e-voting. There are certain countries where in which now the e-voting is happening through the blockchain. So when once the voters cast their votes are getting recorded in the blockchain, providing a degree of transparency as well as the immutability. Healthcare also has potential benefits of blockchain. So if you look at the features, number one, it is distributed in the sense the chain is getting replicated and stored in every node in the blockchain network. It is decentralized. The reason is that there is no central authority to handle the transaction. Every node in the network can participate in validating the transaction. Every node in the network can participate in creation of the blocks, and hence the chains can be created. This is the reason why we call it the blockchain as distributed, decentralized, as well as peer-to-peer network, because peer can communicate directly with each other rather than through a central node. So these are all the various features. And in addition, in terms of security, you have immutability. As I said, when once the transaction is validated and recorded in the chain, typically it is difficult to modify such transactions. And above all that we have transparency and transparency with pseudo anonymity. So transactions are observable, but at the same time, it is also providing the privacy in terms of who is making the transactions and to whom it is the transactions are happening. And in one way, this is having advantages for the users, but at the same time, when it is being used, sometimes there are chances of being used for different other malicious purposes. But the point is, it is able to provide transparency with pseudo anonymity. And there is an important another feature called smart contracts, where in which upon a particular conditions, And when there is a data and the code that is met all the conditions, transactions can be triggered automatically. These are all the various features of the blockchains. At the same time, we also need to understand there are certain myths surrounding the blockchains. Typically, when the students are doing certain projects or trying to make an application, they think that the blockchain is the whole and soul solution for all the problems. But we need to understand that blockchain solve cannot solve. I'm sorry for the typo error. It cannot solve all security issues. It can solve certain security issues in terms of integrity. Okay, but it cannot solve all security issues. And what is the purpose for which it has to be implemented? It should be implemented, but it cannot provide a solution for typically all kind of problems. And also there is another myth that blockchain is nothing but the Bitcoin or even the cryptocurrency, but it is not so. In fact, the cryptocurrency has heavily dependent on the blockchain, but blockchain has multiple other the advantages and use cases. Similarly, people also think that blockchain and distributed databases are similar technologies, but the point is that blockchain can be regarded as a distributed database, but distributed databases are all not blockchains. As I said, your blockchain is a distributed database, but above all that, it has some more features, some more additional advantages, some more the algorithms that are supporting the blockchain. So both are not similar technologies. When you look at the blockchain framework, typically we can also see the blockchain in the form of a layered architecture. Like in the case of our TCP/IP protocol stack, we have 4 or 5 layered protocol stack. In a similar manner, blockchains also can be viewed as a layered approach. If you see on the top, you have application layer wherein which your smart contracts, programmable finances, similarly programmable societies, then chain codes. These are all the typical applications of the blockchain sitting on the topmost layer called application layer. Then next to that, we have consensus layer, wherein which in order to make these blockchains to have verified blocks getting created, we need to have certain consensus among the nodes that are participating in the creation of the blocks. How do I create the consensus? There are certain algorithms. So your consensus layer will take care of creating the consensus among the nodes. One typical example is the proof of work or proof of stake. So these are all proof of authority. So these are all various algorithms that are there in obtaining or creating of the new blocks. And in the network layer, you have peer-to-peer network communications that are happening it. And then in the data layer, typically your blocks are actually getting created. Okay, so where in which you have digital signatures of cryptography that are in place, then the typical data structures such as Merkle trees that are there, then cryptographic hashes are there, your the transactions that need to be pushed into the data blocks, you have the transactions, the timestamps, all these things are part of the data layer. Then at the bottom layer is your virtual machines or the containers wherein which your blocks are getting created. So your hardware layer. So we can see a layer architecture of blockchain in this particular diagram. There are multiple categories of blockchains called public blockchain, private blockchain, consortium based blockchain, as well as the hybrid blockchain. Typically, a public blockchain wherein which everybody can participate, anyone can participate in that particular blockchain, either in creation of the nodes. They can also see either the transactions that are happening. So in fact, it is a totally decentralized. There is no control at all, but at the same time it also has certain drawbacks in the sense that in creation of the blocks it takes enormous amount of time and energy. So public blockchains wherein which anybody can take part, whereas private blockchains typically there is a kind of blockchains that are meant or created by a particular organization, and that means it is closed. no one can, other than that members of that organization or other than the nodes of within that particular organization, the other nodes cannot participate in that blockchain process. So it's called private blockchain. We can say that it is a kind of a centralized or a closed entity wherein which the organization is taking care of maintaining the blockchain. The consortium blockchain is also similar to the private blockchain, but the major difference is that it is not that one organization, rather multiple organizations takes part in maintaining, creating and maintenance of the blockchain. So this is the fundamental difference between consortium and as well as private. Consortium also can be regarded as a private, but the point is that rather than specific to one particular organization, you have multiple organizations taking part in the blockchain process. In addition to that, you have a hybrid blockchains wherein which you have certain features of public, certain features of private. Both are there in the hybrid blockchain. So we have the four different categories of blockchains in place. You can see the timeline of our evolution of the blockchain. All this has started in from 2008 when Nakamoto has published his first paper on bitcoins. If you notice, the typically bitcoins is all about the cryptocurrency, but that means, in fact, the the, the core fundamental principles or technology behind the Bitcoin is the blockchain, which are already there in place. If we say whether in terms of Merkle trees, they are already there. So Nakamoto has come out with a paper on cryptocurrency using the blockchain principles, and subsequently, there is a lot of transformations that have happened both in terms of development of the blockchain technology, its applications, and also in terms of bringing the new currencies. There is a lot of progress that has happened in evaluation of the blockchain. Now, how do we understand, or in order to understand in deeper aspects of blockchain, how do we do it? So people see that, understanding the blockchain seems to be a little complex, but if we can compartmentalize the components that are there in the blockchain, it would be very much easy to get a whole picture of how it is working it. So we need to compartmentalize the whole blockchain into, say, the computer science mechanisms that are there. That means the core data structures, which are nothing but the linked list, the Merkle trees that are there, or even the distributed computing that is there. So that is on one dimension of the blockchain technology. And on the other dimension is about the cryptographic primitives, which includes your public key, asymmetric key technology. Then you have the secure hash algorithms, then the digital signatures. So this is the other dimension. Then the another dimension is about the financial concepts, which are nothing but the ledgers. So all these three aspects, if we can understand, or the three dimensions we can understand, then understanding blockchain technology or blockchains per se would be easy. So first, let us focus on the crypto primitives behind the blockchains. So far, we said there is a component called cryptographic hashes. So what is the hash? Hash is typically, as the shown it in the diagram, hash is a function called a one-way function. Okay. What is the role of this particular one-way function? It is taking a variable length message. It is taking a variable length message as an input, producing a fixed length output called the hash. This is also called as digest. So hash or digest of the message that what is supplied to the hash function. Okay, so it is an algorithm or a function taking a variable length input, producing a fixed length output. So what are the properties or characteristics of this kind of the functions? Number one is the one-way function. It is supposed to be one-way function. That means it is possible whenever you are having a message, it is possible to create the digest, the fixed length hash value. That is one way, but the reverse is not possible. That means when you have the hash value, and when whatever the hash function that is used to create the hash value is known, but knowing the message is not possible. So calculating the digest or the hash is possible from the message, but from the hash value, knowing the message is not possible. This is called one-way function. This is the one-way function property. In addition to that, there are other properties called collision resistance is another property of the or requirement of the hash functions. So as I said, we have the one-way functions. Um, it is a one-way function. It is, as I said, it is computationally infeasible to find the input. That means the message M for which you got the output, which is the digest. You are not able to calculate the input from the given output. Then it is called a one-way function. Okay, the hash algorithms are also regarded as collision resistance. That means imagine if I have a message and its digest called, say, I'm calling it as the hash of M. I should not be able to uh, mm, get another message. Say this is M1 and this is the hash of M1. I should not get another message having the same hash of the HM1. So I should not get it. So I should not get another message which is having the same hash of H of M1. So this is the collision resistance. So it is computationally infeasible to find two or more inputs that are providing the same output. It is called collision resistance. So these are the properties of the hash functions. So to give you a quick understanding, you see here, imagine there are several hash algorithms. The most popular algorithm is the secure hash algorithm, and the algorithm has the version called SHA-256. Of course, we have a SHA-512 as well, where in which the output produces 512-bit output. The example that is shown in the slide is about the SHA-256. Imagine my input is only 1. So you see the SHA-256 digest value, which is the 32 8-bit characters, which are represented in the form of hexadecimal notation. So 32 8-bit characters, which are represented in the form of a hexadecimal notation. Similarly, when my input is 2, you can see the SHA-256 output. Similarly, when my input is hello world, what is the SHA-256 output in the form of hexadecimal representation? So typically, you can see that since it is producing a 256-bit value, so the number of possible digest values, you can see a large number of values. So the number that is shown here is the decimal value. Reading it itself is difficult. It's not in hundreds or thousands or millions and billions. You can see the number of possible digest values. It's a huge number. You can represent in the form of 2 to the power 256 because you are producing 256 output value. So the possible output values are 2 to the power 256. So it's such a large number. And in fact, this number goes much more larger when we implement SHA-512 algorithm. This is on the hashes. The other crypto primitive for blockchain is the asymmetric key crypto technology, wherein which every communicating node will have a pair of keys. So take an example. Imagine there are two people talking to each other, Alice and Bob. In asymmetric cryptography, every node will have a key pair called one is the public key, another one is called private key. Imagine this is Alice and this is Bob. You have public key of Bob as well as private key of Bob. Okay, so is it that I have only a two key based encryption? Of course not. There is a symmetric encryption as well, wherein which communicating parties communicate with the help of a single key. Okay, this is called symmetric key encryption. But our focus is on asymmetric cryptography because the blockchain is heavily dependent on the asymmetric encryption, wherein which every node has a pair of keys. One is public, another one is private. As the name itself implies, the node, the key which is public, the node will keep it as a open, and the key which is private, the node will keep it confidential. Similarly, the all other nodes as well. There are certain properties for these keys that are preparing. A public key and private key both are mathematically related to each other. But the point is, when once everybody knows the public key, calculation of private key from public key is computationally infeasible. That is the one of the fundamental characteristic of asymmetric key cryptography. Otherwise, there is no security at all. But at the same time, both keys should be mathematically related in the sense that when encryption is happening with the help of one particular key, the decryption should be able to be performed with the help of the private key. And that's the reason why we need to have mathematical relation between both of them. So see the example here. Now Bob is sending a message to Alice. Okay, so the message is hello Alice. The encryption is happening with the help of Alice public key. That means encryption is happening with the help of receiver's public key. How the Bob knows the public key of Alice? Because it is a public. And there are other intricacies behind it, because how Bob knows in an authenticated manner, we talk about digital certificates. That is a different concept. But the point is that we are assuming that Bob knows now in an authenticated manner receiver's public key, which is nothing but the Bob's public key. So using the Bob's public key, message is encrypted by Bob and sent to the Alice. Alice would decrypt that particular message with the help of the private key of Alice. Who knows the private key of Alice? Obviously, Alice only knows. That means private key, receiver's private key is used for decryption purpose. Okay, so if you notice closely, this concept of encrypting with the help of receiver's public key, decrypting with the help of receiver's private key provides one of the aspect of cryptography called confidentiality, because no one else can decrypt that message, and to decrypt it, one need to know the private key of the Alice. Only Alice would know it. In that way, the communication is having confidentiality. Now see the other diagram here. Now Alice is sending a message to Bob. Now, when Alice is sending the message, how Alice is doing it, the encryption process, Alice is using her private key. That means the encryption is happening with the sender's private key. Now, is it that I can call it as an encryption? You see what is written here. This is called encryption, but what it is called? This is called signature. So when you are encrypting with the help of sender's private key, what you are doing is not actually an encryption, but actually a signature. So the encrypted piece, you can call it as the signature. So sender's private key is used to sign the message and send the message. What the receiver is doing? Receiver is verifying with the help of sender's public key. Okay. So one has to understand the fundamental difference in these two concepts. When I am de-encrypting with the help of public key of the receiver and decrypting with the help of receiver's private key, I'm able to achieve confidentiality. When I am encrypting with the help of sender's private key, decrypting with the help of sender's public key, what I am achieving is the digital signature. Okay. So this is the fundamental notion that if we understand, the blockchains use this particular concept, wherein which your signatures cryptographically signed blocks. What does it mean? The means is this is the point that is happening it. So sender's private key is used to sign and sender's public key is used for verification purpose. Now the question is it that Bob only can verify the message? Anybody can verify the message. Why? The reason is verification is happening with the help of sender's public key, and sender's public key would be known to everybody. So anybody who wants to verify the transaction, what they can do, who has inserted the transaction, they with the help of their public key, we can verify the transaction. And that's the reason why we are saying that blockchains are providing transparency, because we are able to, anyone can verify the transactions that are sent to the the network. So this is the asymmetric cryptography that is there working behind the the blockchains. So these points in the next slide are all what I will have explained now. In addition to the hashes as well as the the asymmetric key cryptography, we have one more component called message authentication, which is a cryptographic primitive wherein which when there is a sender sending a message, there is an algorithm called message authentication code algorithm, which takes the secret key as an input. In fact, this secret key is nothing but that symmetric key. Okay. And this symmetric key is used to create the message authentication code for the given message. And we get the message authentication code value. And the message as well as the message authentication code value are sent in the communication channel. And at the receiver takes the message. And as I said, since it's a symmetric key, the receiver also should have that same key that is used for the creating a message authentication code. Apply the same key to the message and get the message authentication code value. If the received code value and the calculated code value both are matches, then that means the message is genuine. Otherwise, it is the fake. This is the fundamental principle of message authentication code. And this also would be used in addition along with the digital signatures in the process of blockchain. Okay. Now we have understood so far crypto primitives that are there behind the blockchain. Now let us understand. We said whenever there are transactions, these transactions have to be appended to the blocks. Now let us see what is a transaction. Typically, a transaction is a imagine if there is a transfer of assets, it could be a recording of transfer of assets, digital currency, inventory, whatever the transactions or whatever the communications that happens between the communicating parties, we can call it as a transaction. Let us look at this particular example, where in which a particular user called A is making a transaction to another user account B by transferring certain amount value. Similarly, A is also sending a message, value to C. Okay, A to B and as well as A to C. So this particular transfer of the amount to B as well as C is recorded, and we can call that as a particular transaction, and every transaction would have a transaction ID. And when you have such transactions like this, we can have a block containing multiple transactions. What is the a block can have a single transaction or multiple transaction. Most important thing is determining the validity of the transaction is important. Since there is a transaction, it doesn't mean that the chain would accept it. The transaction should be signed and they have to be verified. Now, the point is when we say that blockchains have the transactions which are signed and can be verified, what are the things that are happening? It is all the crypto primitives what so far we discussed in the previous slides. And remember, anybody should be able to verify the transactions. How they will be able to? Because the transactions are signed by the person, signed by the node along with their help of their private key, and with the help of public key of that node, any other node can verify the transactions. Now we know the transaction. Next, what is a ledger? Ledger contains collection of transactions. Okay, and all these ledgers are stored digitally, and hence large databases, we can call it as a large databases, and owned and operated solely by the trusted third parties. So far the ledgers, banks have the ledgers, any other organizations would have the ledgers, but these ledgers are owned, maintained by the trusted third parties. Okay, but the point is we have now central, these type of central ledgers have various drawbacks. All of us know there is a single point of failure, or how to see that the transactions are valid or not, whether the transactions are complete or not, whether there is any kind of transactions are altered. That means any kind of alterations have happened to the transactions, how to check it. These are all the problems with the traditional ledgers. But when we implement this ledger in the form of a blockchain, we can mitigate all these issues, because we are, number one, making these transactions, putting into the blockchains through distributed consensus mechanism. Okay. So now let us look at this particular diagram, where in which you have node 1, node 2, node 3, and node 4. you can notice that every node is maintaining a ledger. The ledger has, so far now there are 3 transactions. Okay. There are totally 3 transactions. Now what happens? Imagine there is a transaction that is comes in. Okay, so there is a transaction. Now, as of now, there are 3 transactions and a new transaction is coming in this particular node called transaction 4. So that becomes a pending transaction. And remember, so far it is not included in the ledger because it has to be transmitted and to be verified by all the nodes in the network. So in the next step, you can see that the node has kept the transaction in pending and it has transmitted to every other node in the network. Okay, so every node is maintaining that this particular transaction 4 uh, is in pending stage. Then what happens? Every node will include this new transaction in their block only when if any one of these nodes accept that, verify the transaction and accept it. Okay, so you can see that there is one particular node still keeping this transaction in pending. That means there is a delay in updating it, but this will eventually get updated. Let us keep this particular point in mind. We will discuss about this when it comes to the updating of the blockchains. That means, when we have multiple chains, how to handle this issue, or ledger conflicts, how to address this issue. While talking about it, we can discuss it. Now, the point is that you can see that now almost all nodes, these ledgers got updated, right? And remember, this updation happens only when there is a consensus. That means all the nodes accept it. What is the consensus? That we will discuss it. So the transactions are added to the blockchain when a mining node publishes the block, and a block contains set of valid transactions. And how do you ensure the validity? Validity is ensured by checking that, whether, say, take an example, one particular transaction is happening between A to B, whether A is having the sufficient funds in case if there is a transaction about the money, and all that happens because of the cryptographically signed transactions. We will see what do you mean by mining nodes and all that. Okay, a little later. When once you have block is hash, thereby creating the digest which is representing the block, and change of even a single bit would be extremely difficult to change the hash value. Let us see what is a block now. You can see that there is a block that is shown here in this particular slide. The block contains various fields. One is the block header. Sorry. So you can see that the block contains various data fields. One is the called block header and hash. Similarly, the transaction list and the actual block. Okay. So in the block header, you can notice the hash of the previous block. Okay, this is one particular block, and the hash of the previous block, timestamp at which this particular block is created, and nonce. Nonce is a number which we will see little later. What is the significance of nonce? But it is a cryptographically generated number. Uh, um, Let us understand so far as of now in that manner. Then there is hash. What is that hash? Merkle root hash. This also we will discuss little later. What is meant by Merkle root hash? And then hash of this particular block header. So the whole block header is having the hash, and in that you can see what are all the transactions. So transaction 1, so on, etc., etc., etc. So this is the whole block. Okay, so this is one particular block, and once this particular block is created and it gets added to the chain. So if you notice, we are not actually storing the hash of every transaction. Rather, couple of transactions are pooled, and that pooled transactions are stored in the form of a data structure called Merkle tree, and the tree root node hash is stored in the block. So if you see in the previous diagram, what is that it is stored? it is stored as Merkle root hash. Okay. What is Merkle root hash that we will discuss? So this is the Merkle tree. You can see on the slide a tree structure called Merkle tree, wherein which the last nodes, the leaf nodes are all the transactions, are the data elements. So I can call this as transaction 1, transaction 2, transaction 3, and transaction 4, etc., etc., and so on. Now, what happens? How do I create the Merkle tree? So take the all the transactions. For every transaction, now you see here, I'm creating in the next level hash of this particular transaction. Okay, so this is the hash of this transaction 1. This is the hash of the transaction 2. This is hash of transaction 3 and hash of the transaction 4. Then in the next level, the hash of these two hashes. Okay, so this I can call it as hash of H0, H1. So hash of hashes. This is again hash of hashes. What are the hashes? H2, H3. And then what is my root hash? This is the root hash, which is hash of H4, comma H5. So if I have 4 transactions, I can create a Merkle tree of 4 transactions in this particular way. So the bottom row represents the transactions, and the next level is the hash of those transactions. And in the next level, hash of those hashes. Finally, at the root, you have the hash of the tree. This is what actually stored in the blockchain. So you can see this particular diagram which is representing it. So this is one particular block, and this is another block. This is another block. Now you see here what is stored in the block, each block, Merkle root hash. So you have set of transactions which are stored in this particular block. These are the transaction list. I have 1, 2, 3, 4 transactions, and all these 4 transactions, hash of the transactions, again hash of those the hashes, again finally the root hash, and the root hash is stored in the block. Similarly, you see here in this particular block, it is represented hash of the previous block. Okay. And similarly, what about this hash of the previous block? So as we move on in creating the new blocks, you can see that every block gets created with set of transactions and along with the Merkle tree and the Merkle tree root hash and the timestamp linked to the previous block. This is how a chain gets created in the blockchain. So what is the underlying data structure that is used for the blockchain is the Merkle tree. There is another, interestingly, there is one more variant of Merkle tree called Merkle tree is coming in. Recently, it is got proposed. We hope that, maybe that that also would be helpful in creating the blockchains. So whatever I said now is in the next slides. So blocks are chained together through each block containing the hash of the previous block, forming the chain. So the point is, in case, now imagine I have chain in this way, in case if any of the transactions gets altered, the point is a malicious entity is altering the transactions, they have to create the root hash. Then again, link that with the next block, which is computationally very difficult to alter this type of transactions. And hence, we are able to achieve immutability. We can say we are achieving immutability. Is it that impossible? Certainly possible. For a malicious node with an enormous computing power, it is possible to do. But the point is that that particular malicious node has to calculate the entire set of chain. If suppose it alters the transactions, then again create the root hash, then again alter this, so it has to do it. So, but in fact, it is quite difficult to achieve it. Now, we said that there are nodes which are creating the which are taking part in the blockchain creation and operation. Again, the nodes are divided into multiple categories. called full nodes, lightweight nodes, pruned nodes, archival nodes, master nodes, mining nodes, staking nodes, authority nodes. The kind of role these the nodes that are there in the peer-to-peer network, the kind of resources what they have, the responsibility what they have, the kind of consensus mode that these nodes are operating. Based on this, we have the nodes and their categories. I will just skip illustrating each type of nodes because they are available in the literature. But to give you a perspective, it is all dependent on kind of transactions, kind of resources, kind of consensus algorithms, kind of activity these the nodes are participating, whether they are doing a validation. So all this makes various categories of the nodes that are taking part in the blockchain. Now, from the beginning, we talked about a couple of times about consensus. What is meant by consensus? Consensus is about a set of computers taking part in the process called mining, wherein which through this mining, they are agreeing upon the creation of the blocks. Since there is no central authority, that is one of the salient feature of the blockchain. There is no central authority which is creating the blocks and maintaining the blocks, and that means there are multiple parties that are getting involved. The point is that when these multiple parties are getting involved, so node 1, node 2, node 3, node 4, all the nodes are taking part. The point is that the nodes are non-trustable nodes. They don't trust each other. Okay, so they need a process with which they come to a common agreement about creation of the blocks. And where these kind of non-trustable nodes would be there, they would be there in the public blockchains. Typically in the private or a consortium mode of chains, where you have a closed entity, the nodes are trusted. But when it comes to the public blockchains, nodes are not trustable, but they're taking part in the creation of the blocks. So, but how do they come to a common agreement? It is through a process called consensus. Okay. So this particular consensus protocol determines which new block gets added to the chain. This is the purpose of consensus. But how do they come to that? Let us see one particular algorithm, and then we will come to an understanding. So one of the algorithm is called proof of work algorithm, which is the proof of work
Excuse me, doctor.
process. Madam,
Excuse me, doctor. Please check your time. Thank you.
sorry.
Please check the time.
Yeah. Okay,
Yeah.
okay. I think
Are
we
you
are at
finished? Yeah.
yeah,
Okay.
yeah.
Please
So how much time
finish
we have,
speaking.
madam? How much
Actu-
time we
uh,
have?
Actually, it's 2 minutes only, but you can have a little bit, but please try to wind up soon, okay?
Yeah.
Because we
Yeah,
have
yeah.
classes. Thank you so much.
Very good, very good. Okay. So, okay, in such case, I will just quickly give you a perspective of proof of work. Proof of work is the algorithm wherein which nodes have to do some activity. So take an example, we have 4 nodes, node 1, node 2, node 3, and node 4. Now imagine this a particular transaction, or imagine that when a block has to be created, who has to create the block? I have 4 nodes. So if any one of the node or 2 nodes or 3 nodes also create the block. But the point is that to prove that a block has to be added, they have to do certain work. What is the work? Imagine the work is through solving a particular puzzle. Okay, so all the nodes have to solve a particular puzzle. So imagine that I have a set of transaction. In this example is that a transaction is a message called blockchain, and that particular message along with the crypto a random number called nonce is used to create a particular hash value. But is it that I can create any hash? I want any hash value. The condition is that hash value is supposed to be to start with, say, 6 zeros. So I have a message, and the point is, what is the nonce value with which I can combine that with the message, which can create a hash value which is having the leading digits as zeros. So you can see that, the nonce value is given as 0, nonce value is given as 1, and so on, so on, so on. There are multiple numbers that are given. And finally, and with one particular number, you can see that that particular hash value or digest value having leading 6 digits has zeros. So that means a node that is able to identify this particular number, the nonce number, is regarded as the winner. Okay, but how to do that? It is to verify trial and error starting from 0 to that particular number, and hence it demands a lot of computational time. So especially if you notice that previous slide puzzle, it took almost 1,07,30,896 guesses, to make identify that particular nonce. Okay, so this is the proof of work, one particular node. The point is that is it that only one node can solve it? The other nodes also can solve it. But again, when this is a simple example, is it that one node only can solve it? They can even combine with the other nodes to solve a puzzle. So that means imagine I have a network of say 10 nodes, node 1 to node 10. Suppose node 1 and node 2 can join together and guess some numbers from node 1, some numbers from node 2, and finally find which is the nonce. So such type of cooperation between the nodes also is possible. So it's a proof of work algorithm. There is a beautiful example in this particular website, blockchainbasic.com. Those who are interested, they can check it. Along with the proof of work, there are so many other consensus algorithms called proof of stake, delegated proof of stake, round robin, proof of authority. Like this, there are so many algorithms. And during this process of creation of the blocks, there are chances that the multiple chains may come. But only thing is that the finally, whichever is the longest chain, the conflicts would get resolved by keeping the only the longest chain, and all other shorter chains would be discarded. That's how the ledger conflicts would be resolved. So I would actually suggest those who are really interested to look at various other literature such as NIST document and books to get the more details of the the blockchain. Smart contract is another additional feature wherein which there is a between two people. Say, take an example, there is a buyer and there is a seller, there are assets to be transferred, and the set of agreements or the set of conditions to be met to make this transaction happen, that could be programmed, and the smart contract would be taken care of executing this transaction if provided if there is a valid agreements met the condition. There are various platforms for the blockchain. These are all few popular blockchain platforms: Ethereum, Solana, Avalanche. These are all various blockchain platforms, and you can also see the consensus mechanism that these platforms have. You can also see the programming languages, which Solidity is the most preferable programming language. In addition to that, you have a Rust. Majority of these platforms support these um, programming languages. The point is that many times we just tend to misunderstand when to go for a blockchain. So this particular flowchart is a nice illustration of whether to go for a blockchain for our particular application or not. So we need to see all that is the database. Is there any database in our application? If there is no, then first of all, we need not even go for a blockchain. Imagine if there is a kind of a data and the data requires shared write access, then only we can go for the next level of access, the next level of condition, that whether the nodes that are participating are trusted. If they are trusted, then we need not actually even think about going for blockchain. The point is that if they are not trusted only, we can think to the having a blockchain to the next level. The point is that do you want to need to use a trusted third party? If it is no, then do you need a controlled authority? Then no. Then only we can go for either a public blockchain or a private blockchain. In any of these conditions, if they are not meeting, then we need not even go for for a particular blockchain or not. So blockchain market is rapidly increasing it. So the students who are actually interested, there are various job roles that are dependent on the blockchain in terms of blockchain developers, data scientist, blockchain administrator, and what are the technical skills that are needed to meet this particular job roles are also given in this slide. And there are various excellent resources available online. Those who are interested can check these resources. With this, I would like to thank you all for the patient listening, and I hope that this 1 hour session is has given you some brief intro and perspectives of blockchain, fundamental building blocks of the blockchain, crypto primitives, data structure, and how the blocks are created and how the chains are maintained. Thank you.
Uh, Thank you, Dr. Aswani, for sharing with us your knowledge about blockchain. We have learned a lot for such a short time. Thank you for the very concise and clear explanation about blockchain. And I really appreciate your sharing of the flow chart for deciding whether we need to use a blockchain or not and what type of blockchains to use. So now I would like to ask any participant if they would like to ask any questions for Dr. Aswani. Are there any questions, please? Okay, maybe there's no question, but maybe before we wrap up this seminar, I would like to ask you, Doctor, um, how can we use the blockchain technology in academic setting?
Okay, so it's an interesting question. Actually, in academics, there are various ways and applications in the blockchains can be utilized. One of the fundamental aspect is, when the university is issuing the degree certificates, all these certificates can be issued through a blockchain. Okay, so that number one, we can see that the certificates are tamper proof. Anybody can verify the certificates. So that is the one of the fundamental advantage the blockchain can provide to the academic sector. And there are n number of n varieties of other applications. In fact, we have an article. I'll be happy to share it with you.
Oh, okay, thank you, Doctor, for that answer. Let me just share the certificate of appreciation for you. Hold on, please.
So shall I? Yeah.
Sorry. Yeah, can you see the certificate, Doctor? Can you see the certificate?
Yeah, yeah, yes. Yeah,
Okay.
yes. Thank you.
So, the University of Technology and Applied Sciences is awarding this certificate of appreciation to Dr. Aswani Kumar Cherukuri, professor and ACM speaker from the School of Computer Science, Engineering, and Information System, for sharing his valuable knowledge as a resource speaker in exploring blockchain technology at the University of Technology and Applied Sciences Nizwa on 19th of March 2024. So, Doctor, on behalf of Mrs. Suad Al-Riyami, our head of department, and on behalf of Mrs. Sonia Sones, the IT department member for Professional Development Committee, we would like to thank you for your time and for sharing with us your knowledge about blockchain technology. Thank you very much, Doctor.
Thank you. Thank you.
Yes. Thank you, sir.
Thank you. So shall we conclude? Yeah.
Yes. So colleagues, that's it for today. Thank you very much to everyone for attending this seminar. And Miss Sonia will send you the feedback form later on. Thank you very much, everyone. I will now close this Teams meeting. Thank you.